So we continue with chapter 3. And we are at this level. So for the radio network planning, it's really an important step when we want to design a network. The objective is to provide a cost-effective solution for the radio network in terms of coverage, capacity, and quality. So the process typically starts with the collection of some input parameters such as network requirement, capacity, coverage, and the quality, the number of person or users that expected, the type of services, the requirement, and so on. And these input are then used to make the theoretical coverage and capacity plan. That's what we will do using several exercises. So having those, we can find the number of cells or the radio sites that are needed in order to satisfy the requirement in terms of coverage and capacity. And after that, for the radio network planning, we have to select the position of the different cells, and we can allocate the frequencies. And after that, we reach the phase of fixed network planning, where we can design the network. It's possible to make some tuning and to update according to the increase of the traffic, for example, or to some specific dimensioning phase. It could be short term or medium term, and so on. So typically, the planning engineer should try to do very realistic, accurate dimensioning for each cell site. So we'll start by the cell site dimensioning, and after that, when having the number of cells, we can then dimension the radio interface to achieve the communication and the connection between the cells and the base station. Uh, and typically, this radio interface will be in terms of number of channel that are required in order to support the required capacity. Okay, we will see this also in several exercises. And after that, we will see the connection between the base station and the base station controller, which is the A-base interface. It could be typically it could be wireless, or it would be also wired according to the solution adopted by the operator. And after that, we could dimension the A interface, which is between the base station controller and the core network. It's also possible to select or to dimension the base station controller in terms of processing capacity and so on. So how many base station is able to control and so on. And after that, we can also dimension the home location register. So this is the typical dimensioning process done in cellular system. And to do it, we need the geographical area to be covered, the estimated traffic in each region, the minimum requirement of power in each region, the quality of service, which is the blocking criteria. We will see also the path loss according to the environment, the frequency reuse factor. Those are the parameters that are required in order to be able to do the dimensioning in a cellular system. So let's start with a simple example here. If we have, for example, we want to do the evolution of the traffic over a certain period. So typically, it could be from 3 to 6 months, for example, and we can take 2 periods, and we try to see how much the traffic will increase during those 2 periods. So typically, tau c is the increasing factor, and A is the traffic offered, the traffic that we should support in this network. And M as a kind of security margin. So typically, if we want to work without any security margin or without taking into account the increasing of the traffic, so we will do the dimensioning with the traffic A. But typically, if we want to consider the increasing, for example, over 6-month period, so it's better to work with A1 plus 2C, okay? And this, in this case, it's like we are doing dimensioning, taking into account the possible increasing of the traffic over 6 months. If you want also to add a security margin, because you know it's a kind of estimation, so typically it's according to the margin, it could be 5% or 10% or whatever. So in this case, we will work using this traffic AF. So we will do our dimensioning using AF, which is A, taking into account the increasing and then the security margin. So typically we can work using this AF traffic. So what's generally done, the dimensioning of the radio interface, it's an important step. It's an important step because when we dimension the radio interface, it's possible to do the number of cells taking into account the traffic, the offered traffic, and after that to be able to dimension all other part of the network, like the ABS interface, the base station controller, and the other interfaces. So let's start with the traffic channel. Remember that the traffic channel is typically one physical channel on the radio interface. And typically, if we want to take the number of subscriber and the traffic that is generated by each subscriber, so we can have the traffic offered by Erlang. Okay, this is using Erlang, and you know, Erlang it's typically the occupation of one resource during 1 hour. If I say that I have one resource or one channel, and this channel is occupied for 1 hour, this means that the traffic generated in this case is 1 Erlang. Okay, if I have two channels and each of those two channels occupied only a half hour, in this case the total traffic is 1 Erlang because for each channel we have a half hour, so it's 0.5 Erlang, and for two channel it will be 1 Erlang, and so on. Okay, so that's why Erlang it's a well-known unit. In this case, if we have the traffic in Erlang and we have some quality of service criteria, which is typically blocking probability, and after that we apply Erlang formula in order to find the number of the channel that should be used in order to support the traffic, taking into account the quality of service. So I will give you a simple example. Maybe you did this in telephony, but just a kind of, let's say, overview for you. Consider a traffic that's estimated per subscriber to be 30 milli Erlang per subscriber, and it's at peak hour. And the population is estimated that we have 500 subscriber. So what's the number of required channel in order to support this traffic, while the quality of service should be 1%, which is 10 to power minus 2. So typically, the total traffic A here in this case is 30 milli Erlang times the number of subscriber, which are 500. So in this case, it's around 1 milli Erlang. So it's around 15 Erlang. So after that, with 50 Erlang and a blocking probability 10 to power minus 2, we have to check the Erlang table. You can download Erlang table from the files in Teams. So typically I will open the Erlang table, and it's generally it will give us the number of channel that are required in order to support 15 Erlang with a quality of service 10 to power minus 2. Okay, I will give you it's the Erlang table. So based on the Erlang table, it will be around 24. It will be around 24 channel. So we need here 24 channel. It's around 24 channel. Okay. So this is the way, based on the traffic and the quality of service, we find the number of required channel. Okay. So typically this is for the traffic channel. Okay, this is for the traffic channel, and typically we have one traffic channel. If you remember, it's a logical channel which is mapped to one physical channel, which is one IT or time slot. And generally, in this case, if we have 24 uh, channel, in this case, remember that to have 24 channel based on the radio interface, in this case, we should divide the 24 channel, TCA traffic channel. Each one is one physical, so we need 24 time slot. And to have 24 time slot, we need at least divided by 8, we need 3 frequencies. So in order to support the traffic, at least we need 3 frequencies in order to have by each frequency we have 8 time slot. Okay, and then we can support this traffic using 3 frequencies. Okay, this is for the traffic channel. For the signaling channel, let's take the case of SDCCH. It's also possible to calculate the occupation of the SDCCH channel. And typically, as you remember, the SDCH channel was used for all signaling regarding to the establishment of the call and to the location update, and the part that we can use also to transmit SMS. SMS, we can send them using SDCH channel. Okay, that's why in some operator the price of the SMS is not very expensive, because typically they are sending the SMS over signaling channel. And typically this is the occupation of the SDTS channel, and we multiply by the number of users, and we can obtain in the area that we want to dimension the occupation of the SDCH channel. So also using formula Erlang, and according to the quality of service, it could be 10 to power minus 2 as a blocking probability, or 10 to power minus 3. In this case, we can obtain the number of required SDCCH channel, and this is a logical channel. Okay, this is a logical channel, SDCCH channel. Okay. Okay, I have just to So we can continue at this level. And as we said, we have the number of required SDCCH channel. So the objective here is to find the required physical channel. Here, this is the number of SDCCH channel as a logical channel. Okay, so then we know here that SDCCH channel is a kind of signaling channel. Okay, and typically we can multiplex 8 SDCCH channel that are logical on one physical channel. Okay, so that's why for 8 SDCCH channel, we can use only one time slot. So that's why in order to find the number of time slot that we want to use for SDCCH, we divide the number of SDCCH channel over 8. Okay, because here we make a multiplexing of 8 logical SDCCH channel over one physical channel. Okay. And after that, we have the number of TCS channel, the number, those are the physical channel, the number of physical channel or time slot required for SDCCH channel, all other time slot required. We sum all of them and we divide them over 8 in order to find the number of frequencies that want to use. Okay. So that's this is the way we determine the number of transceiver receiver, which is the number of frequencies required to support this traffic. So this is typically the way to do. And I just will give you the examples for SDCCH and for TCH. Okay, it's possible also to do for other signaling channel like paging, okay, and random access, that the calculation will not be very difficult. Just you have to take into consideration the traffic that are supported, the kind of traffic that will be supported using those signaling channel, and you will determine the occupation of those channel based on the number of users, and after that you can find the number of logical channels required for those signaling and then the physical channel. So typically for all other signaling channel that are different from SDCCH, in general we can take because we don't have a lot of signaling occupation, so that's why we can take one time slot for them. So that's why we focus on the exercises on TCH and SDCCH. Okay. So I will try to start by a simple example. Let's start with this exercise. So here we consider a GSM network to cover an area, okay? And in each cell, we have one time slot is reserved for the broadcast channel and 2 time slot are reserved for SDCCH channel. So this is a given. So we have already one time slot which is reserved for the broadcast channel and all other signal channel, for example, and 2 time slots that are reserved for the SDCCH channel. So in this case, the first question is, what's the minimum number of channel needed to serve an area where the potential demand is estimated to 1.6, so it's around 1,600 Erlang for 1% blocking rate. Here in this case, in A, they don't give a reuse factor, so it's a kind of theoretical case where we want to see if we have only, let's say, one area, what's the number of required channel. So typically it's a very simple case because here we have A, which is equal to 1,006 Erlang, and the blocking probability is equal to 10 to power minus 2. We can check the the number of using the Erlang table, and we can find n is equal to 1,683 channel, which is really the physical channel. Okay, I want to give you an approximation. You can use it if you don't have the formula. Typically, if we are working with we have A, and we have the blocking probability in the form of 10 to power minus k. In this case, k is equal to, in our case, it's possible to use an approximation if you don't have the array, the Erlang table. You can use that. In this case, m is equal to a plus k radical a. It's an approximation. And if we approximate here, it will be 1,000 plus 2 radical, and it will be equal to 1,068 channel. Okay, so this is an approximation. It works with where the blocking probability is in form 10 to power minus k. And if you have the Erlang and you want to find the number of required channel. Okay. So let's continue with B. What's the minimum number of GSM base stations required and their respective capacities when the operator has 63 frequencies for a use factor of 9? Okay, in this case, you have the use factor, the cluster size is 9, which means that you have 9 cells in your cluster. Okay, and you are using 63 frequencies for those cells. Okay, so in this case, if you have 63 frequencies over 9 cells, this means that you have 7 frequency per cell. And if you have 7 frequency per cell, this means that you have 7 times 8, you have 56 time slot, which is physical channel. And remember that you have 1 is reserved for the BCCH and 2 are reserved for the STCCH, so that the physical channel that are for the traffic, so we should remove 1 plus 2 BCCH and STCCH, and we have 53 IT or 53 physical channel that are used in each cell to support the traffic. So recall that we have 1,600 Erlang. So in order to see how what's the number of cells that are required, we should find how much a cell can support. So we have 53 IT, which is 53 channel, physical channel, with a blocking probability 10 to power minus 2. This means that the traffic that could be supported by a cell, if we can check the table, it will be 40.6 Erlang that can be supported by cell. So in this case, if you want to find the number of cells, it will be the total traffic over the capacity of each cell. And in this case, we need around 40 cells. Okay, we need around 40 cells. Okay, in this case the 40 cell, and in each cell we have we have 53 physical channel. This means that the total number of channel in this case will be 40 cells times 53 channel. It will be 1,000 or 2,120 channel. Okay, so because we divided into cells, this means that the multiplexing will be with a number of channel that are 53, and in this case, in order to support the whole traffic with the same quality of service, that's why the number of total channel will increase. Okay. If we want to apply for C, so in C, we have the same question. What's the minimum number of GSM base stations required and their respective capacity when the operator has 63 frequencies? But here the reuse factor is 3. When the reuse factor is 3, this means that the cluster size is 3 cells and the 63 frequencies are used by only 3 cells because the reuse factor is 3. I will add a slide here to complete the calculation. And in this case, as we said, reuse factor is equal to 3. So reuse factor is equal 3 and is equal 3 cells. And we have 63 frequencies over 3. We have 21 frequency per cell. For each frequency, remember that it's 8 physical channel. So we have, in this case, 21 times 8 will give 168 IT. And remember that in each cell, we have 3 minus 1 plus 2, 1 for BCCH and 2 for SDCCH. So we have 165 IT, which is physical channel. Okay, so in each cell, so what's the capacity per cell? So we have in each cell 156 channel, and the quality of service is 10 to power minus 2. So this means that we are able, based on the table, to support 145.9 Erlang. Okay, that are supported by a cell. The number of cells in this case is the total traffic that want to support over the capacity of each cell, and it will be around 11 cells. Okay, the total number of channel are 11 cells, and by each cell it will be 100. It is 100 times 155, and it will equal to 1815 cells. Okay, here, because we are using the reuse factor of 3, okay, a reuse factor of 3, we need 1815 cells. Here we are using a reuse factor of 9. We need more cells because the number of frequencies per cell or the number of channel per cell is less. And here the case 1, it's like we are using a cluster size equal 1. It's mean that we are using 1 cell. So in practice, it's not possible to have a big cell over a country, for example. So, but it's a theoretical assumption just to see that we have reuse factor equal 1 here, and all the traffic is on 1 cell. So this means that in this cell, we need 1680 channel, which is also less than the value before. And this will let you understand that if we have more resources, that we are using them by a lot of users with the same quality of service. So at each time we have more resources to be shared between or multiplexed between the users, it's possible to have less required if we have more resources, it's possible to support more traffic, for example. So here, for the same quality of service, because we divide the quality of service, the 10 to power minus 2 over cells. So when the cluster size increase, this means that the number of required channel in total to satisfy the quality of service will increase. And this is the case. For n equal 1, it was this number. For n equal 3, it was around 1,800. And for n equal 9, it's around 2,000. Okay. So I hope it was clear for you how to find the number of cells. So let's move to another exercise where here we want to calculate for one cell, for example, or an area, and we want to see how to calculate the, let's say, the traffic. Okay, so let's start by consider an area to serve that's characterized by the following parameter. We have the density of 1,000 subscriber per kilometer, and we have 0.5 kilometer, and we have the mean duration time of communication is around 90 seconds. Okay, the incoming call rate is around 0.5 call per busy hour. The outgoing call rate is about 0.6 call per busy hour. And the incoming call successfully is 0.8, the outgoing is 0.65, and the blocking probability is 1%, which is 10 to power minus 2. So what's the total traffic of the area at busy hour? So here we want to find the total traffic. So we have, let's say, we have the number of subscriber is equal to rho times S. It will be 500 subscriber because we have half kilometer square and we have 1,000 per kilometer. And let's see the traffic per subscriber. Here we have, let's say for the incoming call, we have a rate lambda 0.5 call per hour times the rate of successfully it's 0.8. And when it's okay, in this case, we have 90 seconds over the 1 hour is 3,600 seconds. So this will be during the busy hour. And for the outgoing call, we have 0.6 call per hour times 0.65 the successful rate. And it's also 90 times over. Okay, so if we calculate this value, we obtain 19.75 millierlong. And the total traffic in this case will be 500 times 19.45 millierlong, and it will equal 9.875 erlang. If we want to use this to support this traffic with a blocking probability of 10 to power minus 2, we have the number of required channel based on the table is around 18 traffic channel. So this is the number of traffic channel that needed to serve this area. Okay. If you want to see part C, what becomes the number of traffic channel needed to serve this area if the market share of the operator is around 40%. So in this case, we consider that the operator is in charge of only 40%. This means that you have other operators with the market within this market. So typically, instead of calculating the number of traffic for the whole traffic, we should just calculate it for 40%. Okay, so we should take 0.4 times this value, and after that, applying the Erlang formula and finding the number of channels. It will be less than 80. You can do it. Okay. So I want to ask you to try to make this exercise just to be sure that you are able to understand what we are doing, and I will try to give you the solution in the next session. Okay. And here, after finding the let's say the number of cells and the number of let's say channel and cells, after that we should dimension the base station controller. How to dimension the base station controller? It's the equipment that we want to implement. So based on the capacity, connection capacity and the processing capacity. So how many base station this base station controller is able to control. يعني عندنا نحن كم سيل بدنا نحط. شوف base station controller, شوف الداتا sheet. It's a kind of technical data regarding this equipment, and based on that we can dimension. For example, I can select one base station controller to control 3 cells or 4 cells according to the data supported or the user supported in each cell. In some case, it's possible to be 2 cells according to the user supported and so on. And typically, it's the maximum number of base station supported, the maximum number of trial call, the maximum number of TRX, the frequencies that could be supported, the maximum port number, and the maximum number of signaling link. Okay, those are typically the parameters that are used in order to dimension the base station controller. So typically you will receive a data sheet, technical data sheet regarding the equipment, and based on the number of cells, you can decide that those 3 cells could be supported by this equipment, others could be supported by another equipment, and so on. So after that, so when you dimension the base station controller, you need to dimension the interface, which is the link between the base station controller, and the link between the base station controller and the core network. And this is what we call link dimension. And typically we are using E1 link. بتكونوا شفتون أعتقد بالتليفوني E1 links. Okay. And it's typically T1 in USA and E1 in Europe, and typically is 32 time slot, and typically one frame it's around 8 time slot of 16 kilobits per second for each of them. So if you want to take 4 time slot, okay, it's around 64 kilobits per second, and it's 1 time slot for radio. It's radio. Okay, so that's why. If we want to take this one is the radio, okay, because we are working with GSM here, and this is the 1 time slot at link 1. Okay, so that's why we have for each 4 time slot radio frame for each 4 radio frame time slot, we need one time slot from the link E1. So that's why in order to find the capacity of the ABS interface, so we could divide the number of radio frames, of radio time slot, okay, over 4. Okay, and here we obtain, when we divide over 4, we obtain the number of time slot needed at the link E1. In order to know how many, in this case, how many link we need, we should divide by 30, because there is 2 are used for signaling. So that's why we divide by 30 and not by 32. Okay, so maybe you did some dimensioning like this. So typically, according to the radio time slot we have, or radio physical channel we have, okay, thus this number of radio physical channel, according to the cells we want to support over this link, we divide the total number of the physical channel over 4. We obtain the total number of the physical slot or the time slot at the E1 link. And after that, to see the number of required E1 link, we divide by 30. Okay. So this is an example here, as we said, for each 4 time slot at the radio interface. UM is the radio interface. It's one IT link E1 interface. At here also it's the same. However, for A interface, it's possible to use what we call a transcoding rate and adaptation unit. And in this case, it's used in order to make an adaptation of the communication with the classical telephony, which is the ISDN system. And typically, the speech in ISDN system is 64 kilobits per second. So that's why we expand the voice encoded in GSM to be 64 kilobits per second. And in this case, the 4 time slot at the radio interface will be equal to 4 time slot at the link E1. So this means that 1 time slot radio will be 1 time slot at link E1 because we did an adaptation unit here. Okay, and that's why it's possible also to find that TRU may be between the BTS and the base station control. It's possible to do it, and in some implementation, this TRU will be close to a mobile switch center in the same, let's say, physical location, and this will help to have the connection here over 4, divided over 4. Okay. So this is generally the how to dimension those links. Now we arrive at the mobile switch center. So just to summarize, we determine the number of cells. Okay. After that, based on the capacity of them, we decided which which base station controller, and this is base station controller and the capacity of each of them. And after that, we make the dimension of the link to connect them. And now we arrive at the mobile switch center and how to dimension the mobile switch center. So we need to take into consideration the connection, the capacity of the connection, the commutation, the switching, and the processing, the number of users that are supported by this mobile switch center, the maximum number of base station controllers that could be supported, the maximum number of call trial, the maximum number of signaling links that are controlled, and the maximum number of port. And based on the data sheet provided, we can decide if we can use one equipment for mobile switch center, or it's possible to use two mobile switch center that are distributed geographically according to the architecture adopted by the operator. Okay. So it's possible to have more than mobile switch center. Okay. And I will stop here because we should continue with link budget. So maybe we can do it in the next session. Okay. So I hope that you will be able to do exercise 3. Okay. I will start by doing this exercise next session. Okay. And then we continue the link budget. And if you have any question, you can ask. Please, you can review the lecture note. You have a lot of details in the lecture note, but the exercises here are complementary to the part given in the course. Okay. Thank you.